So we've discussed block convolution and the idea that we can take one long convolution and convert it to multiple smaller convolutions. And we've also shown that an FFT, appropriately zero-padded, can be used to make the convolution of a single block very efficient. So let's put all this together and run through an example and see if we can figure out how much more efficient this is and when it makes sense to go to the extra trouble. So we'll start by assuming that we have an H rather, a filter of length n, and X is length m, and we'll assume that m is much larger than n for this particular example. And we're going to choose a block length the same size as H, our filter. And also, just for convenience, we'll assume that m is equal to r times L, or in other words, we have that the number of segments is equal to m over n. Okay, so if we were to directly compute the convolution, the output of this, y is equal to h convolved with x, that would be m times n multiplies. So, but we have this great idea. Why don't we do this in smaller blocks? That should be better, right? So if direct convolution is used, or direct computation is used with block convolution, then the output, the number of multiplies for each block will be L times L. Length of a block is L, which actually in this case is equal to n. Okay? So n total multiplies. And we have to do that r times. So the total multiplies can be found as r times L times L. But we already know that that's equal to m, and that's equal to n. So we get m times n. Well, that's what we had before. So one thing that's really nice to know is that it's less computation. I mean, not less computation. It's not more computation. But the sad thing is it's not less computation either. So now let's consider what happens if we do FFT-based convolution for each of those blocks. So in this case, we have to do a bunch of computations. It's a little bit more complicated. The first one is an FFT of H. Now H is length n, and so and we'll have to do a FFT of each of the R segments, the X sub R segments. In order to make this work, if H is length n and R is length n, X of R is length n, then we're going to have to do a 2n, actually a 2n minus 1, but let's just round it right now to make the math just a little bit easier. And you could know that maybe you could save 0.5% someplace in the total computation if we did things correctly. By the way, often, even, for example, it might make sense to choose n so that 2n minus 1 is length 2, or a power of 2 to the n. Then our FFT would be efficient. But we can't have 2 times an integer minus 1 being another even number. So it just doesn't work. So we're going to round it up. And the inverse FFT is also going to be the same length, as is the product. Okay, so how many computations does each take? This is going to be about log 2n. And remember, this is an approximation. It may be a little bit more efficient than this. That FFT and that inverse FFT, the inverse FFT will actually have a little bit more to it because it has the scaling factor of 1 over n that we have to take care of. But just to get a quick big picture of what's going on, the multiply itself has to be taken into account, and that's 2n multiplies. So let's count all this up. We have 1, 2, 3 times that, plus we have essentially total mults is 2n, 3 log 2 of 2n plus 1. And you can use the laws of logs to take care of that just a little bit. However, this is assuming that, so this is the output for a single stage. But in reality, we're actually going to compute the FFT of h just one time. So when we're doing the whole computation, that's not going to be factored in there each time. Because we're using the same FFT. So that gives us a little bit better expression of 2n times 2 log 2 n plus 3. Okay, so I did two things here. First is I took out one of these computations, made that a 2. And the second is I pulled the 2 out. Log 2, base 2 of 2 is 1, times 2 is 2, added to the 1 already in the expression, and that's where we got the 3 on the right-hand side. So the approximate complexity is going to be n times 2 actually, yeah, it's what I just wrote above. In my notes, I took several steps to get there, and now we're there. Okay. It should also be noted that we have this 1 over n that we have to take care of with the inverse FFT. We can incorporate that into our FFT of h. Put in a scaling factor of 1 over n, so we don't have to apply it at each stage. The multiplication by h is going to take care of it for us. So the total approximate complexity is just equal to 4 Rn 2 plus log 2 n. I'm sorry, not 2 plus log 2n, but 3 halves log 2n. And that's equal to 4m log 2 of n plus 3 halves. You know what? We're just going to approximate that as 2. Make calculations easier. Okay, so when is this more efficient? This is more efficient if this quantity here is less than m times n. So it makes sense to go through all this problem if it saves computation. If for n, or for log 2 of n plus, I don't know, 6, 8. I guess we didn't have to make that easier. We'll just take that out. 4 times that plus 6 is less than n. Now, it should be noted that if we're right there on the border, just do the straight convolution, because from a computational point of view, computers are much more efficient at just accessing data in a nice linear fashion. And this involves doing a whole lot of different types of computation, which means the overhead is a problem. So when does this happen? When n is, let's see, approximately, we want log 2 of n to be less than n over 4, approximately, and this happens when, this will happen somewhere around n is equal to 8. In practice, I wouldn't probably go this way until n was 32 or 64 or something like that. And then you'll start to see some big savings.